Yay. Okay, so let's keep trucking. So we talked about a whole bunch of Microsoft operating systems last time, kind of the evolution of those guys. We talked about kind of how the actual operating system is something called a kernel. That's what's under the hood. All these things that we typically refer to as operating systems are actually distributions. Doesn't really matter. Big picture, kind of unimportant to this class. You'll kind of see how these things are going to start angling towards this class here pretty quickly. Today is a fun thing that I'm guessing most of you, at least those of you who've never had my class before, haven't heard. How many of you like Apple? Okay. Or like their Apple stuff, whatever. You might not like the company. There's any old big evil company. How many of you hate Apple? Any Apple haters in here? It's not going to bother me just because I have a Mac up here. I run Windows on it too. No Apple haters. All right. So, you heard of Steve Jobs, the Apple guy, right? Well, he's dead now, but before that, he was the founder of Apple, right? We kind of mentioned last time when we were talking about that Microsoft was licensing their software. So Microsoft kind of invented the idea of licensing software, right? So this was a major transition in the computer science world when Microsoft kind of supplanted IBM. IBM's quote was, the real money's in the hardware. Microsoft started licensing software on a per purchase basis, and they became a $1 zillion company. The rest is history. So now software is kind of where things are. Hence, we're sitting here in this coding class. Not that hardware isn't still important, but more and more things are just running on software. Because our hardware really, for most things, has become fast enough. So in the early days of Apple, early-ish days of Apple, they were licensing DOS as well for the old Apple computers. Now, those of you in here who have an Apple computer, you have a Macintosh, right? A Mac. So they don't actually have Apple computers anymore. Years ago, inside of Apple, they had two different teams competing with each other. You had the Apple team, which was all running DOS. And then you had the Mac team, the Macintosh team, which was running a modified version of operating system they got from Xerox, which I think I mentioned last time. So Xerox decided real money's in the copy machines. So they bailed on personal computers, gave Apple their software, first computer that had like a mouse type thing. So kind of the invention of our modern day graphical user interfaces, GUIs. Not that there wasn't some light things that had existed before then, but in terms of full commercial use, Apple, let's say, was the first one that put it in front of people. Okay, but internally at Apple, they had two different teams competing with each other, the Apple team and the Macintosh team. If you've ever read or watched any biography stuff on Steve Jobs, you probably learned pretty quickly he wasn't the most pleasant guy to be around. Hard to work for, very passionate. I kind of like to think of it like, not a very well-rounded person, but in order to change the world as much as some of these people have, they kind of needed to be crazy, so passionate about the thing that he was passionate about. Well, so he was spending a lot of his time working on the Macintosh side of things. So stepped down as CEO of Apple to focus on Macintosh and hired CEO of Pepsi, I think, to come and run Apple. Now, Apple is a publicly traded company, like a lot of companies are, which means they're run by a board. So all of a sudden, they fire Steve Jobs from his own company. They can do that as a publicly traded company. So Steve Jobs is out on his butt. All right. So now there's some question. What did Steve Jobs do during that period of time? Because when he died, he was back with Apple, right? I'm going to say sort of. But he must have gone and done something once he was fired from Apple. What did he do? Go ahead. Yeah. So He had a buddy, George Lucas, going through an expensive divorce. Had a little company called Pixar. Probably haven't heard of it, I'm assuming. I think he bought Pixar for something like $7 million and sold it for a lot more than that to Disney Corp and stayed in control of the company because he ran the board. That's a pretty good deal, right? Here's $7 million. Somebody then gives you $8 billion back and still lets you run the company. Pretty good deal. Okay, so he flipped that. What else did he do? Let's look at a little picture here. Next, computers, Steve Jobs. There he is. We get a big picture of that. Oh, guess it didn't really give me. So that's Steve Jobs. After he was fired from Apple, he created a new seems like I should probably get off this page pretty quick before we get some strange pop-ups. Went and founded this company called Next Computers, which was back at this period of time, one of the major problems with personal computers as they were becoming more and more prevalent in homes, was the incompatibility between DOS, DOS machines, even Windows machines later on, and Macintosh machines. So if you had your floppy disk and you had it formatted in a PC and you went and put it into a Mac, it would say, I can't read this disk. Do you want to format it? So moving data between those incompatible machines was not convenient. Now you put your USB stick into any of the machines, it pops up, no problem. But that used to be a major, major issue. And back then, the idea of emailing yourself an attachment wasn't really a thing. This is before the internet, or at the very least in the early-ish days of the internet, where email wasn't something that was just on every computer. You couldn't just hit a random website and pull down your email. Everything was text-based. You'd use a program called Pine to check your email, stuff like that. Well, anyways, so Steve Jobs is off creating this new computer, a new company called Next Computers. Spent a lot of money. There's some story behind the logo. He spent zillions of dollars on this logo. I don't know, there's some trivia thing behind it. Like, it was a ridiculous amount he spent on the logo for some reason. Actually made some money with Next, selling it to universities. It was running on, it was a Unix-based operating system, pretty stable operating system with a graphical user interface. And one of the things that it was bragging about was that it was you could put Windows, it could read Windows or Mac formatted stuff. It could do other things, but let's just leave it at that. Downside was it was pretty expensive. All right, so pause the Next Computers thing and go back over to Apple. Apple has always been known, has usually been known as a proprietary company. What does proprietary mean? What do we mean when we say a company is proprietary? And is it a good thing? So proprietary means only their stuff, right? Their stuff works with their stuff, and they own the special sauce. They don't share it with anybody else. If you're buying a Macintosh computer, you're buying it from Apple, right? All right, so their stuff was proprietary. You see it in some like foreign cars and things like that, where you got to take your car to a special shop that only works with that kind of vehicle because they have parts that are not readily available, that kind of stuff, and everything's more expensive, all that jazz. So in general, when you hear the word proprietary, is it fair to say we kind of view that negatively? Okay. So Apple was getting some pressure. This must have been in the mid-90s-ish. Yeah, somewhere in the maybe 93, 94. They were getting some pressure to open source, so you can get Macintosh compatible hardware. So you weren't just buying your Mac computer, your Power PC back then. You weren't just buying it from Apple. You could buy it from third-party vendors who would make the hardware. Now, when Apple went and did this, they almost failed as a company. Whole bunch of other things kind of went down, but they almost fell apart as a company. Part of Apple's special sauce, and I think I kind of mentioned this last time, or at least alluded to it, is the fact that they're proprietary. I mentioned that Microsoft really is solving a pretty impressive and difficult problem with Microsoft Windows, right? They're writing an operating system that runs on thousands and thousands of different configurations of computers with different processors, different brand and speed memory, hard drives, yada, yada, yada. And it, for the most part, works great, right? Yeah, you get the occasional crashes, whatever, but in general, Windows 11 is a good operating system. And it's solving a very difficult problem. Apple is solving a much easier problem in that they're only writing software for their own hardware. Well, they went down a path during that period of time, and this is with their old operating system, which they had very fancy naming conventions for. You had OS 6, then you had OS 7, then you had OS 8, and then you had OS 9. That we hadn't gotten into the cats and stuff yet. And that's kind of where we're going with this. So Apple goes and does this and basically almost fails as a company. So what did they do when they were almost failing as a company? Somehow Steve Jobs got back over to Apple, right? What if I told you he never actually came back to Apple? So when Apple was failing as a company, they went back to Steve Jobs. Obviously, it was his baby, probably didn't want to see it fail, had an opportunity to get back in there. Now, when big companies have smaller companies, so Next Computers relative to Apple was a very small company, right? And that big company decides we're interested in the small company, what do? They buy it, acquire that company, right? Okay, so they acquired Next Computer for a song. And with that came Next Computer CEO, which was Steve Jobs. And then they installed Steve Jobs as the interim CEO of Apple. All right. Which then later he started being called the iCEO, because from that point forward, he turned Apple around, right? With all the iPhone, the iPad, the iMac, the blah, 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 the everything, right? And they brought him out of, out of death. But the reality is Apple actually did die. And what we see today is actually Next Computers with an Apple logo on it. Now, from a programming perspective, we can see this when we look at some programming documentation. So here's some documentation for, and one of the things that's going to be very, very important as a coder, I mentioned the first day of class that programming is the skill set, the language does not matter, which means that we're going to, once we learn kind of those basics for what every computer program can do, we are going to be able to immediately learn a new language and start working with it. And part of what's required for doing that is being able to read documentation. And you're going to find that most coding documentation is laid out pretty similarly to each other. And we're going to learn skills in here that allow us to read that documentation. Again, that's a superpower. Debugging your code is a superpower. The syntax itself is nothing special. But in any case here, we are looking at one of the data types in programming for the Mac. And this exists in all of their modern languages, even their newest language, Swift. So for Mac OS, when you're writing code and you want to store a string, like the string hello world, the data type for that, in Java, the data type for that is a string with capital S. C#, the data type for that is string with a lowercase s, earth-shattering. For the Mac, in their various languages, it's called an NS string. To this day, NS stands for next step. This is all code from Next Computers that's sitting there in their underlying API to this day. So what ended up happening is, and you saw this in that same transition, Modern day, those of you who are running Macs today, you're running one of the flavors of Mac OS X, right? So somewhere in there, we had this transition where we had OS at the time during this merger. OS 9 was the newest OS from Mac, and OS 9 was terrible. It was I mean, far inferior to Microsoft's operating systems at the time. It was kind of famous for you'd have a computer running with OS 9, you'd come back the next day and the mouse and everything worked, so you can move the mouse around. The rest of the computer was completely dead. But you were moving the mouse around on top of basically a screenshot. You didn't even get the blue screen of death. It just stopped. And you'd have to hard reboot it and things like that. It was really a bad operating system. Well, next thing you know, Apple releases Mac OS X. Well, then there was all this controversy. Does the X stand for Unix, or does the X stand for 10? Something like that. And the reason for that, so here I'm just going to say Mac OS 6 through 9, old Mac OSs. Then all of a sudden we had Mac OS X. Is this a 10 or the X in Unix? I don't know if we ever necessarily find out. If you look at Apple's naming conventions, they definitely have the number associated with the current version of the Mac OS with 10 dot. So if I say about this Mac, this is running, well, actually, this is running 13.4.1. So this is Mac OS 13. The early days of Mac OS X, it was Mac OS X, Mac OS 10 dot something. So at the very least, behind the hood, it had a 10 there. Okay, but Mac OS 9 was the direct update to Mac OS 8. That means all your software that was running on Mac OS 8, for the most part, ran on Mac OS 9. Well, all of a sudden, they come out with Mac OS X. Whether the X represented Unix or not, the operating system was a Unix-based operating system. So let's pause here for a second and talk about geeky stuff a little bit. I'm going to go a little bit out of order here. So typically when we talk about modern operating or modern computer programming languages, our more powerful languages, we'll talk about the difference between these, are compiled languages. All right. Compiling is turning, let's call it programming code, into the appropriate machine code for the associated architecture and operating system. Okay, so let's talk about these two things, and then we're going to look at some code. When we talk about the architecture of a computer, what are we talking about? Okay, so when I write a C++ program like we're going to be writing in here, and we compile that program, it's going to be compiling that program for the operating system you're running it on, as well as the computer architecture you're running it on. When I say computer architecture, what am I talking about? Build of what? Well, so operating system is the second part. So we definitely need to know what operating system we're targeting, and we'll talk about why here in a minute. But the architecture itself is like the type of processor, right? So if you're a Windows user today, all of your processors are the old, they're Intel compatible processors, right? Whether they're made by Intel or whether they're made by AMD, they're Intel compatible. That means they're running the i386 assembly language. Okay, well, what does that mean? Did I already have that? Okay, yeah. So let's bounce to this one here. And I'm just going to move this. We'll move this right here. So I said 3 kinds of programming languages. We have machine language. We're going back a couple of classes ago, right? We have machine language, which is a bunch of zeros and ones. And I made the little crack about, nobody wants to sit there with the 2-button keyboard. Okay. Not for us. Cool to say you did it once so you understand what's going on. And I promise you, if you don't know how to work with binary and stuff, we're going to learn that in here. And fair warning, if every Lippmann test you have, even through your senior year, will have conversion questions on it to go from binary to octal to hexadecimal and all sorts of different speed sizes. So these are core computer programming, core computer science skills that are related to programming. But I can tell you right now, none of you are ever going to have a job where you're banging out zeros and ones. Okay. And then we have a low-level language. So remember we talked about CPUs. We said CPUs are kind of like this collection of magic tricks. They know how to do 1,000 little tiny things. And if we put those things together, something real happens. That was when we did the little exercise when, move your thumb, do different things. And all of a sudden you put enough of those ninja moves together, you can pick up the mug. So a low-level language has a 1-to-1 relationship with the CPU. What that means is every instruction in a low-level language corresponds to exactly one magic trick on the CPU. So if we put that into real life terms, if we're writing code in a low-level language, usually these are called assembly languages, and we're going through that exercise of, we learned about our different ninja moves here, right? My couple of moving parts, that's the Lippmann CPU, let's say. An assembly program will be telling me each little move to make and when to make it in order to pick up a muck. So you're really getting down and saying, call this little magic trick, followed by this little magic trick, followed by this little magic trick, so on and so forth. Okay. Now it's interesting, but even then, that's getting pretty tedious, even for, again, it's cool when you do it the first time. And we're going to look at assembly code here in a second. But after that, you really appreciate human beings like power tools, right? Would you rather use a little manual screwdriver or one of the screw guns? When you do it in drywall at high speed, just rip right through the wall. Pat, have you ever done that? I've done that multiple times. Not using the right tool for the job, but using the most powerful tool you have that could do the job. All right, so we like high-level languages. This has a one-to-many relationship with the CPU. Okay. So now, what we're going to do is we are going to, so let me bounce back up here to the previous slide. We're going to see these things in action. So we have this idea of compiling a program. These are for our compiled languages. We'll talk about those more, but effectively when I say compiled languages, I'm talking about C, C++, Java, C#, any of the .NET languages. There's some little nuance in there with .NET languages and Java, and as far as compiling goes, we'll talk about that, but those are compiled languages. Objective-C on the Mac side and Swift. Those are your core compiled languages. You don't see new compiled languages coming out very often. Compiled languages typically translate to programs that run fast. So the main use of our compiled languages today tend to be for like writing operating systems, writing video games, that kind of stuff. Then we have this whole collection of interpreted languages that you've heard of like Python and PHP. These are all interpreted languages, that technically have to go through some middleman before the CPU is told what to do. And the idea is if it has to go through a translator, an interpreter in the middle, that means slower, right? Okay. Which is true, but our computers are really, really, really fast. So slower is probably still fast enough for 99% of the stuff we do. But if you're writing video games, that explosion doesn't happen at 3,000 frames a second, we're not happy, right? So for our high performance computing stuff, we're still using compiled languages, but more and more we're transitioning to interpreted languages. Right now, I'm focusing on this idea of a compiled language. You write this program. So in this case, I'm going to write a program. So here, we're going to go very old school. We're going to write it in a terminal here. All right. So we're going to do VI CSC 200 dot. Yeah, we'll do CPP. All right. So we're going to write a C++ program here. Your very first C++ program, which is going to be the proverbial hello world program. All right. So the top, and we'll talk about this in some level of detail at some point. Well, maybe I want to do this in C, but whatever. All right. So I'm going to say int. And this might not work out at your terminal if you don't have a C++ compiler installed. So it's not important that you follow this. Standard lib for that. So let's do that. All right, let's see if that guy does it. All right, so I wrote my code. I'm including input output stream, which is the thing that lets us write to the screen. Then I'm using this thing called namespace standard. If I don't use that, then I would have to do that guy before the out. These are unimportant things for you right now. So I'm going to just bring that locally. I'm creating a program. Start all programs begin and end with main. You're going to hear that from me many times moving forward, whatever this stuff is. And then ultimately, we are going to write something. We're going to output something to the screen. The function inside of IO stream for that is called cout. All right. So I'll go ahead and I save that file. So now we want to compile that file. So I have a compiler on here called G++. This is the GNU C++ compiler. Okay. And I'm going to compile that program. All right. So it compiled that program. Now you don't see anything that's there, but what it just did is it created this file called a.out, which is the executable file that it just produced for me. All right. So if I run that, there's my hello world. So we just saw the full process of writing a C++ program that does hello world, compiling it, and then executing it. And we got hello world on the screen here. Make sense? All right. So now we would look at that code and say, oh, well, that's not that much code, right? So we're going to say this is a high level language. We're using power tools here, even though this is a very simple program. All right. Now, go back in here. And let's just do Linux, hello world, assembly. Let's see, is this one give me a good one? Yeah, good enough. All right, can we read this okay? This is great stuff. So when we compile that program, as part of that middle step, some couple different things happen in there, but we're just going to say that a compiler requires two pieces of information, the architecture. So what kind of CPU will this run on? And the operating system. What OS will this run on? Okay. Why do we need to know about the kind of CPU it's going to run on? So if we think modernly, we could say, because now we've gone back the other direction. This is part of the Apple story, but modernly, if you're on a PC running Windows, you're probably running either an Intel chip of some flavor or an AMD chip of some flavor, right? If you're on a Mac, A more modern Mac, you're running either an M1 or an M2 chip because Apple's gone back to their own silicon, but for a long time there, they were running Intel chips as well. Okay. A long time ago, Apple used to run on these chips called PowerPC chips, which were made by IBM. And then they were becoming hard to produce. So then they started running on, that's when they switched over to Intel. And now they switched back. But we'll talk about that transition here in a few minutes. Let's get this stuff knocked out first. All right. But each architecture for a CPU has its own assembly language, has its own collection of little magic tricks that we can tell the CPU what to do. So Intel-based architectures, that's what this guy is. This is an i386 based architecture. So this is called old school Intel. Every single time Intel comes out with a new processor, it's backwards compatible with all the old magic tricks. Sometimes they'll get rid of some magic tricks, which is why when you look at the requirements for some software, it might say minimum CPU, Intel Core i5, 5th generation, something like that. That means it's anything before that is missing one of those magic tricks that this software requires, something along those lines. But generally speaking, each year when Intel comes out with their new processor, it's largely backwards compatible with last year's processor. Typically, what they do is they just either optimize some of the old magic tricks, but they keep the name, or they add some additional magic tricks. Well, but the processors keep this, every year for a long time now, they've been basically the same size. Well, what have we gotten better at? If you build computers, you've probably seen things like 10 nanometer technology, 6 nanometer technology, seen things like that before? What does that mean? Other than just cool, like giving people specs of your computer and you just throwing out tech terms, not really knowing what they are. What does it mean to have 6 nanometer technology in your processor?
A lot more use in smaller space.
Okay. Why? What's the nanometer thing? Right. But 6 nanometers means that what is 6 nanometers this year compared to 10 nanometers last year? What are we doing better? You're on it. You say we got more stuff in the same space, more effective. We have the ability when we're printing circuit boards to put wires next to closer and closer and closer to each other without causing interference. Our manufacturing technology is getting better and better and better. Go ahead. We're already there. Yeah, that's why this year it might be 6 instead of 5. Because you try to put them any closer together, you start getting a heat problem. They start interfering with each other, creating bugs, things like that. But I mean, you're right. At this point, I mean, we've gone from 150 nanometer in the earlier days, whittling it down. At some point, you're only going to get to some fraction of 1 nanometer, right? That's the best you're ever going to do. And at that point, are we really squeezing more stuff onto our processors? Do we need to put more magic tricks onto our processors? Our processors are already pretty fast, right? We don't really, for most applications, we don't really need to make individual processors any faster. So what have we seen? If you look at the specs on processors today versus the specs on processors, pick your poison, 12, 13 years ago, one thing you'll notice is that the gigahertz, let's call it the speed of the processor, has not drastically changed in the last 12 to 15 years. What has changed? If you have a process, when you buy a new Intel Core i5 processor today, as opposed to an Intel Core i5 processor 7 years ago, what's likely to be the difference today versus 7 years ago, besides a few extra magic tricks that they've added each year? Possibly power efficiency. But when you're looking at the specs of it, something you see in modern day processors is there typically are more cores. Talked about cores a little bit last class or something like that. So, we're not getting any better at putting things closer together inside the processor. We're not getting any better at speeding up the processors without it creating too much heat. So what do? We just put more processors on the slab that we're putting there. So we started off with a single processor. We had single core CPUs. We haven't seen those in years. Okay, but that used to be the only kind of process there was. Then all of a sudden we had dual core CPUs. Dual core CPU could technically do two things at once, as long as those two things weren't incompatible with each other, right? So for example, in real life, you can't bake the lasagna until you've prepared the lasagna, right? You can't do those two tasks at the same time. One task is reliant on the other one being complete. So not every task can benefit from multiple cores. I think I probably used the example of shoveling snow or something like that versus changing a light bulb a couple classes ago. Okay, so more cores doesn't always mean better, but for certain applications, it can mean a lot better. But that's something we've gotten better at over the years as we keep put more and more cores onto our processors. But even there, we're eventually going to start running out of benefits from more cores, right? I mean, even if you're doing something that benefits from multiple cores, is there really a drastic jump from an 8-core processor to a 100-core processor in terms of things that you might do even for a heavy user? Probably not, right? At some point, you're looking at saving 3 seconds on some task when you left the room anyways, as it was converting a video or something like that. All right, some tasks you can only divide up so much. We're shoveling campus. Shoveling snow on campus. There is some limit for the number of students you get involved with shovels before it becomes harder to manage than just working with the 30 people we found, right? 60 isn't necessarily going to be that much better. Is that you got too many chefs in the kitchen or something like that. All right. So these assembly languages are a low-level language where every line of code translates to exactly one instruction, one magic trick on that CPU. All right. So every single computer architecture has an associated assembly language. So if you're running a Windows machine today, you're running an Intel compatible processor, and there is an assembly language associated with that processor that is, it might be missing, depending on what age processor you have, it's 3 years old, you might not be able to take advantage of the 3 or 4 magic tricks they've added since then. But in general, the assembly language for an Intel processor today looks like the assembly language for the Intel processor a decade ago. Okay. So when we're compiling, we need to know what architecture are we targeting, because ultimately what a compiler does is it converts a high-level language like C++, like we wrote, into a low-level language assembly, like we're going to look at here. All right. You also then need to know the operating system that it's going to run on. Why do you need to know the operating system? What is an operating system again? Talked about it a couple classes ago. We mentioned it's kind of that software that sits between the human being and the computer, so we don't have to manipulate things, turning on and off vacuum tubes and stuff like that. So it makes computers convenient for human beings to run, to use, right? Now, do we have an expectation, do you think, over the last 30 years, as our operating system, every year, do we have an expectation as a user for our operating systems to keep getting better and better and better, whatever that might mean to us, right? Things that our operating systems can do today, we were talking about with the Windows stuff, things we take for granted, like multitasking, that kind of stuff, didn't exist that long ago, right? So things that we completely take for granted has only been here for a little bit. And I'm sure if we fast forward 5 years, there's going to be things that we're not even doing today, probably things involving artificial intelligence and stuff like that built into your operating systems that are going to become commonplace. But today, you're messing with things like ChatGPT and stuff like that on websites. But, eventually we're going to learn how to integrate. The hope is we learn how to integrate those things into a productivity model for us rather than a model for, shortcutting things. So how many of you in here have used ChatGPT before? All right. How many of you have ever used ChatGPT to do homework for a class? All right. Because that's what you see on the news, right? It comes out and says, oh, you can just tell ChatGPT, hey, write me a 7-page paper on topic XYZ, yada, 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 all these things, right? And then you turn it in, and as long as your teacher doesn't catch you, you've probably saved yourself, what, 5-6 hours? So that's helpful then, until later on, especially if it was a reasonable assignment. I'm not an advocate for busy work, but let's say it was a good assignment that was meant for you to learn something during that assignment. When you use ChatGPT to get you saved yourself time today, but you missed out on learning something along the way, right? Which then probably translates into you performing more, poorly on the exams or whatever, or missing some piece of information later on. So at the end of the day, you're only hurting yourself, is the punchline. But obviously, that's the stuff that makes the news today. So when in higher ed, well, not just higher ed, all academia, one of the things that the teachers are trying to figure out is how do we police against ChatGPT and similar, right? I mean, I'm of the opinion that it doesn't matter. Why? I'm not going to sit here and look for cheaters. I'll find out on the exam if you didn't learn crap, right? Because you're going to find out pretty quick. ChatGPT is better at coding than it is at writing papers. It's ridiculous how good it is. And the thing is that you can use it once you learn the programming skills, and then it all of a sudden becomes grunt work for you, right? When you're a good enough programmer where you can look at a problem and say, you know what? I know exactly how to solve that problem. I know I can throw 2 hours at it and it will be done, right? It's just a time type thing, not a I need to learn something type thing. Make sense? That's when you can start leveraging things like ChatGPT to say, hey, write me some code. For example, I in the coding 2 class, we're going to work with a game engine in there. And last year we wrote kind of a dungeon crawler, Dungeons and Dragons-y type thing. And and after your guy kills the monster, kills the boss, he jumps up and down for like 30 seconds with a little animation, whatever. That's something that's not overly hard to do in Unity, but takes some time. It's kind of, I don't know, meticulous. So that's something that we might go to the AI and say, write me a Unity C# script that takes a rigid body and makes it jump up and down in the air for 30 seconds, something like that. The more context you give it, the better, and it'll pump out the code to do that. You paste it in, you see how it works by default. Now you have the programming skill sets. You go and tweak it to do exactly what you want it to do. Those are legitimate uses for AI because now you are augmenting your productivity with a tool to save yourself time, not to cheat yourself out of knowledge. All right. I promise you, almost any homework assignment I give you in here, you could probably, and I encourage you to test it, you could probably copy and paste the assignment directly into ChatGPT, and 15 seconds later, you'll have a solution to the homework. That very likely works or comes very close to working. Turn it in. I don't care. I'm going to find out in the exam that you didn't learn anything, right? And the exams are worth, if you remember, a big chunk of your grade. Okay. So from my perspective, your teachers don't really need to learn how to police against students using ChatGPT. We just need to make sure that we're correctly assessing you on the things you were supposed to learn in the class, so that if you want to use ChatGPT to, take a weekend off or something like that, you do you. You're all adults. So maybe at some point between then and the exam, you'll go back and learn the stuff you were supposed to learn. It doesn't matter to me, and I don't know why it matters to so many teachers, but in any case, tools like that are likely going to be built into our operating systems sooner rather than later, right? If you haven't used ChatGPT, I strongly encourage you to check it out. It's ridiculous. They'll scare the crap out of you. Some of the stuff it can do. I mean, it's better than a human in many, many, many cases. I use it commonly, like if I have like a blob of text that I need to extract like a couple of pieces of information from. Example, my brother was in town this weekend, and my brother is a real estate investor, and he goes to a lot of sheriff sales for like foreclosed properties and things like that. So he gets like, you know, call it 200 emails a week, each one advertising some sheriff sale. Well, each one of these might be like, I don't know, two-page paper, something like that, if you want to think about the amount of text. So for each one of those, he has to read through, or at least, you know, skim with paying attention, because he is interested in the location, the date, who the lawyer associated with it is, then maybe 2 or 3 other pieces of information, whatever it is. So let's call it 5 pieces of information hidden somewhere inside of a 2-page paper. Well, you can say to ChatGPT, pick out these 5 pieces of information. You got to make sure you word it right to get ChatGPT to do what you want. Then you paste that 2-page paper in after it. You press enter, poof, there's your 5 pieces of information. Pulls it out for you. So you didn't have to read the stuff. That's a great tool that helps with productivity, right? He knows he can throw 45 seconds of reading at this thing and get something done. But it's a lot easier to just copy and paste it and hit enter. All right. But in any case, when we think about what an operating system is, it goes deeper than just giving us the ability to work with a computer without having to get down to the hardware level. All the people that write software for that computer, the operating system is also supporting the software writers by giving them power tools. Usually these are called system calls. So a collection of system calls that make common, let's put that in double quotes, OS stuff more convenient. And this guy was what assembly language are we outputting? All right. So let's take something fairly trivial, like writing something to the screen. So we go back here, we ran my program, and we got hello world written to the screen right there, right? In our minds, writing something to the screen seems like a trivial task. What do you think is actually happening behind the scenes between the processor determining what should be written to the screen and ultimately getting these pixels lit up on the computer monitor, having to pass through the graphics card, having to pass through all these other things? Do you imagine it's actually far more complicated than we think to ultimately get some pixels to light up on the screen? There's a lot of moving parts there, a shocking amount of moving parts. And if we had to write that every single time, or if our compilers had to output that every single time, the size of our software would get very, very, very large. Because you imagine that most programs are doing a lot more than just writing something to the screen, right? So if writing something to the screen is far more complex behind the scenes than you imagine, how complex do you think the more complex things are behind the scenes? Even more. So it gets pretty scary. So all of our modern operating systems have a collection of system calls. We've actually taken this outside of operating systems, and typically these are called APIs. Okay, and almost every tool has an API associated with it, where programmers can leverage it through a programming API. For instance, ChatGPT, you can go to their website, and you can type stuff in and press enter and just use ChatGPT from a consumer perspective. Or you can integrate things like ChatGPT into your own programs by talking to their API behind the scenes, sending your request to the API processes it and sends you the answer, and they charge you, some fraction of a dime or something like that per 100 words or whatever it is. Okay, so Google Maps has an API, Yelp has an API, so you can pull information from these. Many of them are free. All right, but as you become a more and more advanced programmer, you start realizing that you can start leveraging these third-party things to get stuff done. Okay, so He doesn't charge any of his stuff at home, do you? Do you charge any of your things at home, or you just have a bad battery?
I think they just have.
So anyways, in operating systems, the API is the collection of system calls. All right. So let's go and look at that Hello World program in Linux. First thing I'm going to tell you is, I promise you, you're going to see it as we walk through here, this is using power tools. If you were actually having to write every magic trick it took to write Hello World out to the screen on your computer without using one of the system calls, you'd be writing thousands of instructions, where each instruction corresponds to a single magic trick on that CPU. It's not quite the 0 or 1 thing, but from a human being's perspective, it's pretty close. It's just as bad, right? All right, so let's walk through this and see what's actually happening, so you'll understand how operating systems actually work under the hood. All right, so forget about this top crap. This is where the program starts. Okay, that's just fluff. So here, we're starting the program. So this is our actual code. The actual code we're going to look at is right here, and then right down here. Now remember, I think we mentioned it already, how human beings solve problems. Remember stuff, asking questions, repetition. We've said that, right? All right. So first thing, any programming language will have facilities for those 3 things, including assembly language. It's a programming language. So way down here at the bottom, we're remembering a couple of things. One of the things we're remembering is the thing we want to write out to the screen, Hello World. The other thing we're remembering here is the length of Hello World. It's kind of important in older programming to know, because really what you get here is you get the location of that H. This guy will tell you, how many steps forward do I need to go in order to capture all of the characters that you want to output to the screen? That's why having that length is important. We'll talk about that more many times, but that's what we're remembering here. Remembering 2 pieces of information. What do we write into the screen and how long is it? Okay, so now we move up here. Our computer processors, they have something on there called hardware registers. You can think of these as little tiny variables, places to remember stuff built out of hardware. They're really fast. They're typically small relative to the storage we think about with our like hard drives and our standard computer memory, but it's really fast. In general, when you talk about computer architecture, the closer the memory is to the CPU, the faster it is, the smaller it is, and the more expensive it is per bit. You're just looking at it from that perspective. Hardware registers live on the CPU. Very fast. Okay? But these guys are tiny, so you typically store a single piece of information in them. So EDX, ECX, EBX, EAX, these are the names of 4 little storage locations on the processor, 4 different hardware registers. So we are randomly moving the length of our string into this little storage container. The pointer to the beginning of our string, the location of that H in this case, into this little storage container. Then we're just putting a number 1 into this storage container. And we're putting the number 4 into this storage container. What we're doing here is we are effectively staging our data. Staging the parameters we need to pass to a function in 4 little locations. What are we putting in here? We're saying, how long is what I'm going to write? What am I writing? Where do you want me to write it to? A 1 relates to something called standard output, which on most operating systems is the monitor. So we want to write this out to the monitor. And then number 4 is, which system call do you want me to use? And the number 4 is associated with a system call on, in this case, Linux. We're looking at Linux assembly code here. Intel-based Linux assembly code. So this is Intel instructions utilizing the underlying Linux system calls. So we want to use the syswrite system call, which is the thing that came with the Linux operating system for writing stuff out to the screen or writing stuff out somewhere. It's the same thing to write it out to a file, writing out to wherever. That's why it requires us to tell it where we're going to write it out to. All right. So syswrite, in order for it to work, needs 4 pieces of information. What do you want me to write? How long is it? Where am I writing it to? Well, it needs 3 pieces of information. Okay. Now, right here, we're calling an interrupt. We're telling our CPU that we want it to call upon the operating system. This is how you do this in Linux. Call upon the operating system and have it take over from there. So this is us telling the kernel to go do its thing. And what does the kernel do? The very first thing it does is it looks inside of EAX. It wants to find out, what is it you want me to do? So when it looks inside of EAX, it sees that you put a 4 in there. Then Linux says, okay, well, 4 is which of my magic tricks, which of my system calls? It's syswrite. Okay, well, now I'm going to need 3 pieces of information. So the next thing it does is it looks in those 3 buckets. So it's going to look in EBX to get where are you writing it to? It's important that you've put those values in those specific registers. The syswrite call requires that EBX holds the where, ECX holds the message, and EDX holds the length. It's reliant on those things. So you had to make sure you stage them in the right place. All right. So when the operating system takes over, it looks here and says, what do you want me to do? You want to do a syswrite. Cool. Where do you want to write out to? Good choice. You want to write out to sysout. What do you want to write? This guy? How long is it? This guy. And when you do this here, poof, it pops out on the screen using this power tool right here, syswrite. Then what happens? We bounce back out. They're changing the value of EBX to a 0, which actually isn't even required. But they're just changing it from a 1, which was sysout, to a 0, which is nothing. We're not writing it out anyways. But the more important thing for us to look at here is the EAX. Because remember, when we ask the kernel to take over, the very first place it looks is EAX to find out, what do you want to do? Up here, it wanted to use syswrite. Well, then we change EAX from a 4 to a 1. And 1 is sysexit, which means program die. All right, so then we call the processor again. It checks out EAX. It says, oh, you want the program to exit. Fine. Kills off the program. Doesn't actually need any input. So I'm not sure why they put a 0 in EBX, but maybe it's for an error code or something like that. Probably is for an error code. When you look at C++ code, here, all programs begin and end with main, but this guy can return an integer. And if you don't put something in there, by default, it'll return a 0, which is everything went fine. You ever been on web pages and you get an error that says, error 400 or something like that, page not found, that kind of stuff? Well, this is the old school version of this, where your program can return a number indicating what bad thing happened, if any. 0 usually means nothing bad happened. Otherwise, you get some other error code that, you might show to the user or whatever. Okay, so as human beings, we want to write stuff that looks like that. A compiler ultimately will turn it into, well, somewhere in the middle, it actually turns it into something like this, which then actually gets linked with the operating system to produce a executable file that the operating system knows how to run. So in Windows, that would be some file with a .exe at the end of it. Okay, that when you double click it, it does all the right magic. So it creates that executable. Right, but this is what's actually happening under the hood. So if you were to be a Linux assembly language programmer and you wanted to write hello world, you would write something like this. which does not look that bad. It doesn't look friendly. It doesn't necessarily look like something you'd want to do day in, day out, especially if it takes that much just to write hello world. But you're still using power tools here rather than having to write every little magic trick. All right. But again, human beings want the most convenient process for us. We're not meeting computers halfway. You know, we're coming 0.1% of the way. That's what takes us from normal human being to geek, right? And then the computer has to come 99.9% of the way here for us to talk to it. Make some sense? So as computer scientists today, we're still going to learn what's happening under the hood. What's happening with the zeros and ones, what's happening with the assembly language, because that's an important thing when you go and start solving harder problems. But from an applied perspective, you're going to be using these high-level languages to boss a computer around to have it do your bidding. All right, that's what's happening. But we see for such a small program, that Hello World program, what it's producing is fairly geeky, I guess. All right, so that's what's happening under the hood. All right, so that's the idea of compiling. So back to the Apple story here. Apple made two, I would call it extremely scary moves after they acquired Next Computers. I've already shown you that today Apple is Next Computers with an Apple logo on it. We see it at their programming API level. Stuff is still called Next Step this, Next Step that. We also saw it at their operating system level. So we could put under this and say Mac OS 8/9. This is prior to Steve Jobs' return. Mac OS X was post Steve Jobs' return. And what was Mac OS X? This was the next OS with a fancy Apple front end on it. The original front end was called Aqua. All right. But now, related to what we just talked about, we have a problem. Problem with Mac OS X. So just like if you were a Windows 10 user, and then Windows 11 comes out and you upgrade, your expectation is that most of your stuff that worked yesterday still works, right? Microsoft Word still opens up, your web browser still work, whatever. Every now and then there might be some older application that has some problems. And what does Windows do? They have some things like you can run stuff in compatibility mode and stuff, so it tries to fake it for you. But in general, the expectation is when a new operating system comes out, most of your stuff still works. Okay. The problem with Mac OS X is all of your existing Apple software was compiled for the time. It was the PowerPC architecture. So not Intel, it was called PowerPC. And OS 9. Remember, compiling requires both of those things. So all your programs know how to run on the PowerPC architecture using the system calls of OS 9. The day you installed OS X, you lost all of your OS 9 system calls. Because it was not an upgrade to OS 9. It was a brand new operating system. OS X was based on OpenBSD Unix, not OS 9. So all of the applications that were running on your computer won't run on Mac OS X. Day one, OS X ran on a PowerPC processor. So you had the right architecture to run it, but you didn't have the right operating system to run it. So you were reliant on all of those software producers to potentially rewrite portions of it, usually having to rewrite significant portions of it, and then recompile for the right operating system, which took time. And as you might imagine, even back then, Apple was not all that great at collaborating with those other people. So they kind of dropped this bomb on all of these software companies, say, hey, all of you Apple users, here's the brand new amazing operating system where only the programs the distribution shipped with works. All your other crap doesn't even start. Problem? Probably a problem. Apple shipped OS X with something called Blue Box. Anybody know what Blue Box was? This emulated OS 9. So effectively, you would put OS X in your computer, and then to run any of your software, you had to run OS 9 inside of OS X to run Microsoft Word. And you imagine that probably ran slow, right? Because you were emulating the old operating system inside of the new operating system. So it kind of let you hobble along. But from a speed perspective, performance perspective, you were far better off running those programs natively on OS 9 on your same computer. But nope, you've already upgraded. You got OS X on there, you're stuck. Well, finally, after too long, most software applications were, it's usually called ported to Mac OS X. And really, it was a very, very, very successful operating system. As I mentioned earlier, OS 9 was problematic. You'd have the thing with lockup almost daily. OS X, based on Unix, they took it from the right place. So Microsoft's not the only ones who steal stuff. Sometimes they steal it. Sometimes they buy it or make some negotiations. But all these big companies, they take what they want and then settle outside of court. It's the way business is done, I guess. Okay, so don't demonize any of them. They all do the same crap. All right, so Mac OS X, they got their operating system from OpenBSD, which is an open source Unix thing, and then made it their own by making it look pretty or whatever for Mac OS X, but under the hood, it was Unix. All right, so now all these software companies got their stuff ported over. Life is good again for a couple years. That was a big risk Apple took, right? They saw the writing on the wall that OS 9 was it wasn't cutting it. And to release a brand new to release an operating system that was an upgrade to OS 9 was just going to drag all of the stability problems of OS 9 with it. So Macintosh had to rip off the Band-Aid and say, we need to make the change. It probably did not do a very good job of letting their consumers know that none of their stuff was going to work. A lot of people freaked out, but most people who are Mac fans are drinking the Kool-Aid, so they weren't freaked out enough to jump ship. So lucky for them. But anyways, Apple took a big risk, and in the end, paid off. Now, if you're Apple, you probably think, hey, we lucked out there, right? Well, but then they did it again. They repeated this risky choice when they changed from PowerPC architecture to Intel. So now you buy your newest, latest, greatest Mac. It comes with OS X that they had ported to Intel. So now there's two versions of OS X. There's an OS X that runs on Intel architecture on your Mac computer, and an OS X that runs on PowerPC, IBM's architecture, on a Mac computer. Okay, but those are two different hardware solutions. And I'll just finish up here in the last couple seconds. All right. So again, You went out and you bought your brand new MacBook Pro or whatever the latest, greatest Mac was at the time. I think they were still just MacBooks. All right. And you got your fresh Intel processor. Everybody's excited. And once again, none of your software works. Because all that software was compiled for, yes, the right operating system, but now the wrong architecture. So we got to go through the whole thing again. And it worked again. Apple keeps dodging these bullets. And then what did they do a couple years ago? They went back to their own architecture. Now they have their M1 chips, their M2 chips, yada, yada, yada. So we'll pick up there next time. All right, one thing I am going to put up for kind of like a first homework assignment is for everybody to get onto our Slack channel. So if you're not already on our Slack channel, I'll put up a thing for, it'll be an assignment due for Thursday, that you follow a 3-minute video, go and sign up for Slack, get into our channel and join the CS200 page. Sound good?
Yep.
That'll get you, make sure you have access to Blackboard and all that stuff. All right, I will see everybody on Thursday.